Good morning, everyone. Welcome to, good morning. You can hear me now? How about my voice?
No.
Oh, really?
How about this?
You can hear my voice?
What? Just a moment.
Tito, you can hear my voice? Everyone?
Dengar.
Okay.
Halo? Good morning, everyone. You can hear me, my voice, my sound? No?
Hello, can you hear me?
Okay, I can hear you.
Okay, I can hear you. Okay, thank you. I will start for this event today. Good morning, everyone. I hope we have a good mood and for this event will run smoothly. I will introduce our speaker today. First, we have Mr. Bibi Ardi Sufianto as a graphic design lecturer. And then we have Mr. Sergey Chopro from Zaporizhzhia National University. And I will introduce myself also. My name is Novita, will be moderator and also MC at this event. And I hope this event will be enjoyable and worthy of knowledge. Before we start opening for another speech, I would love to tell you that we will play, So we will pray first according to your own religion and belief. So everyone, let's pray start. Pray finish. Yeah, for the next session, we have opening speech by Mr. Widi. Yeah, for Mr. Widi, you can start. Thank you.
Okay, thank you, Ms. Novita. Good morning, ladies and gentlemen. Thank you for the time. The Honorable Mr. Joseph Teguh Santoso, as a Rector of Stekom University, Mr. Sergey Choprov, as a Doctor of Technical Science Professor from Zaporizhzhia National University, Mrs. Alina Osol, as a Head of International Relations from Zaporizhzhia National University, and Ms. Anggi Novitasari as a moderator for today, and also all of distinguished guests. Good morning, ladies and gentlemen. Thank you to each and every one of you being here today at this wonderful place. My name is VP Ardi Alfianto. As a graphic design lecturer from Stekom University, it is such an honor for me to speak on behalf of the organizer. Let me begin by giving you a warm welcome to the event visiting lecture today. May I first take this occasion to pay tribute to all of the audience of this visiting lecture from Zaporizhzhia National University, Ukraine, to University of Science of Computer Technology, Stekom University. It is a great pleasure and honor for me to deliver this opening speech of visiting lecturer. May I first take this opportunity to express my gratitude and appreciation, as well as extend a cordial welcome to all of the audience in today's event. Good afternoon to each one of you who designed today. It is a moment of extreme pleasure to welcome the guests who are present here to attend this event of official nature on behalf of Stekom University in event today. We will learn about very interesting and useful material by all of us from speaker as a professor from Zaporizhzhia National University. I hope this visiting lecture today will help for all audience have a beneficial for all audience. I offer my regards to Dr. Joseph Teguh Santoso as our director of Stekom University and professor from Zaporizhzhia National University, Ukraine, and also all audience. The visiting lecture will be held in 6 series for 6 days. I wish this event enlighten us all and provide us with approach to deal with the problem of tomorrow. Thank you to everyone who made this manifest this visiting lecture even possible, and for specification, especially for the student of Stekom. Please enjoy this event, take some notes, ask questions, and we play together. Thank you. Well, I don't want to take too much of your time. I need to hand over it to Ms. Novita, our today's MC, to introduce our guest speakers to all of you. I would like to say once more on behalf of this seminar organizer, welcome. It is great to see you, so many of you here. Thank you. Thank you very much.
Yeah, thank you for Mr. Wibi. And the next section, we have Mr. Sergi Chopro from Zaporizhzhia National University. Yeah, for Mr. Sergi, you can start for this class. Thank you.
Hello, ladies and gentlemen. Can you see my presentation?
Yes, we can see.
Okay. Let's start. So, dear ladies and gentlemen, dear students, dear colleagues, today I'm going to discuss with you the topic that I called R functions in geometric modeling. I'm not sure that all the people listening to my lecture yesterday, so I would like a bit introduce myself at the beginning of our discussion. As you know, my name is Sergey Choparov. I am the head of computer science department in Zaporizhzhia National University. My scientific degree is Doctor of Technical Science. It is the highest scientific degree in Ukraine. My researches are devoted to different fields of mathematical modeling, computer-aided design, neural networks, evolutionary methods, etc. I wrote many scientific publications, and I work with students as well. I teach students on both bachelor, master, and PhD levels. I teach my students to create databases, to create web applications as well, to write scientific software, etc. To discuss today's topic, I'm going to use the following plan. After a brief introduction to describe key notions of our functions, and next to show possible primitives and examples on both to model both two-dimensional and three-dimensional objects. The topic that we are discussing today is devoted to the area of geometric modeling known as solid modeling. It is a consistent set of principles for mathematical and computer modeling of three-dimensional solids. The notion solid or solid modeling as practiced today was developed in the early to mid of 1970s years in response to a very specific need for informational completeness in mechanical geometric modeling systems. Solid modeling was conceived as a universal technology for developing engineering languages and systems that must guarantee and maintain their integrity in the following precise sense. Any constructed representation should be valid in the sense that it should correspond to some real physical object. Any constructed representation should also present unambiguously the corresponding physical object. The representation should support, at least in principle, any and all geometric queries that may be asked for the corresponding physical object. Two well-known researchers in the field of solid modeling, named Rick Wisha, the first one, and the second one, Walker, proposed a modeling paradigm that you can see in the figure at the current slide. This figure shaped the field of solid modeling as we know it today. The real-world artifacts and the associated processes are abstracted by postulated mathematical models. The space of mathematical models and operations serves as the definition for the corresponding data type that can be represented on a computer in more than one way, probably, but by one representation scheme in terms of researchers require and Walker. Formally, a representation scheme can be defined as a mapping from a computer data structure to a well-defined mathematical object. Finally, representation schemes and accompanying algorithms are organized into systems and software applications that emulate the behavior of the real-world artifacts and processes. Developing the representation scheme, we can follow following observations. All manufactured mechanical components have a finite size, like this one. Have finite size. We can measure it. They should also have well-behaved boundaries, so we can see that it's finite boundaries that can be displayed and manipulated on a computer. The initial focus was on the rigid parts made of homogeneous isotropic material that could be added or removed. These postulated properties can be translated into properties of subsets of three-dimensional Euclidean space. These properties also lead us to the notion of R set. closed, regular, semi-analytic, and bounded sets are called R sets. By such sets that I repeat it again, that is closed, regular, and semi-analytic, we can, and bounded, we can mathematically we can define such object from the mathematical point of view. There are few ways to represent R sets from the mathematical point of view. We can enumerate all points that belong to the R set. Alternatively, we can implicitly define the set given rules for testing which points belong to set and which are not. As you can see at the picture at the slide, for example, the square sized 2 times 2, we can define implicitly in two ways. For example, we can use the system of inequalities, and we can use one inequality. A very general method for defining a set of points is to specify a predicate that can be evaluated on any point of this space. This predicate can be specified formally as the following formula. In other words, the set X is defined implicitly to consist of all those points that satisfy the condition specified by the predicate A, all those points P. The simplest form of the predicate is the condition on the sign of some real value function f resulting in the familiar representations of sets by equalities and inequalities. For example, if we define function f, as you can see as at the current slide, then conditions f is equal to 0, f is greater or equal to 0, and finally f is less than 0, represent respectively a plane, the first one, a plane, a closed linear half space, and the last one, this one, represents an open linear half space. This very simple observation leads us to possibility of using the inequalities like the second one to define our sets. We can suppose that that any body in Euclidean space, any R set in Euclidean space, could be defined as the following formula, as some real value function that greater or equal to 0. Alternatively, not alternatively, in addition, we can suppose that negation, so outer part of this set, is equal like minus function f greater or 0 to or equal to 0. More complex functions that, for example, this one that defines square at the plane, more complex functions can be employed to define progressively more complex geometric shapes, giving rise to the whole discipline of implicit modeling. A natural approach for semi-analytic sets is to define more complex predicates constructively using logical combinations of simple primitives, which is equivalent to using the standard set operations on sets defined by primitive predicates. we can define the standard set operations union between two sets by formulas, as you can see at the current slide. Intersection of two R sets, this one formula. It's quite simple formulas. And in total, we can say that we can use the following formulas for negation, for conjunction, and for disjunction, where alpha in general some real value function in the interval from -1 to 1. In many real tasks, alpha is selected as equal to 0. For example, defining the primitives for plane objects, we can define the simple formula for line, not for line. The simple formula for line defines some half space behind this line, specified by 2 points. In the same way, we can define ellipse, formula for ellipse with a center at the beginning of coordinate system, the circle of the specified radius, and the circle and some convex polygon as conjunction of lines defined on points that are placed in the corners of our convex. Using the convex function, we can define a regular polygon, and just defining the rule to place points on the plane. We can define the rectangle as the conjunction of two stripes, vertical and horizontal, of specified words and height, where stripe is also some implicit function defined below. And finally, we can define in this section rectangle with circular corners using the following formula, with limitation on error and values of words and height. For example, conjunction of two rectangles can define simple L-shaped figure with dimensions that you can see at the current slide. This plot shows how this function is distributed in the region. We can see that it gets positive values in the middle of this region, and 0, it is equal to 0 on the boundary, and it will be less than 0 or negative on at all points out of its shape. So it's very simple rule to check whether point is belong to this figure or not. In the same way, we can define, for example, plate with rectangular cutout, just using conjunction of rectangle and with negation of regular polygon with 3 points. This function also is positive in the in internal points is equal to 0 at boundary. I don't show how it distributed out, but it will be negative out of the region. Another one example, the knot section, knot-like section, it could be defined like union, like the conjunction between regular polygon of 6 nodes and outer part of circle. It's typical for any knot in mechanical. We can define using such formulas, for example, transmission friction clutch plate, that such plates are used in transmission systems of cars, and we use the same primitive functions, but we add additional mu function that this function makes copies of its argument of some region. It's something like it's mathematical analog of copy operation in computer science. And we can see final model of clutch, and it's drawing. In the same way, we can define primitives to model three-dimensional objects. For example, the first one defines some half space defined by 3 points p1, p second, and p third. This function defines ellipsoid, three-dimensional analog of the ellipse shape. This function defines a sphere in 3 dimensions. In both two last cases, we have the center of figure in the origin point of the coordinate system, but we can easily translate just adding or subtracting coordinates from x, y, y, and z. This one function is well-known cylinder. As we can define as conjunction of circle and stripe in the z axis. In this case, we will have cylinder with originally plane that we create cylinder moving circle within zx, and polyhedron is multiple conjunctions of planes defined on points of polyhedron, and absolutely the same to rectangle. We have shape for cuboid as three-dimensional parallelepipedized object. For example, using two-dimensional knot, we can define three-dimensional function, adding bevel function and adding function that defines thread for our knot. And you can see how it looks in section, how function is distributed in internal points of knot. we printed such object. We printed this discrete object generated for this function on a three-dimensional printer, and it's not could be connected with any join. You can use in any standard join with bolt. It's okay. For example, another one, three-dimensional example, is a piston that could be also defined using standard primitives by its directions. The piston from the real car manufactured in our country in 19th years. This car is known in our country by the title Tavria. And concluding, this mathematical background, this mathematical basics can be employed in many areas of applications in computer-aided design, in computer-aided engineering, as a pre-processing tool in the finite element analysis, in 3D printing to define the geometry of printing object. I want to show you how it could looks. To use such mathematical background in modeling of object, we develop the special software, but the way it's open source software that allows let's open some. For example, that allows to describe the shape using the domain-specific language. It's in the current case, it's some subset of Java script-like languages. Using conjunction, disjunction, and our primitive functions, we can define as well open implicit function, and to build finally some discrete model. Some discrete model, like can you see? And we can see now how function, implicit function, is distributed in this region. Or alternatively, not alternatively, or in addition, I want to show you. We used this software and such approach to model space structures as well. It's more complex solution. No, it's to generate something. this example you saw as well. It's our with triangle discretized. I want to see how. We can use this one. Typically, we use such approach not to define only the shape of the object, but to perform the finite element analysis of the stress strain state of the object. I want to show you some quick example how we do it. We define the shape by our function using the domain-specific language. We define as well all boundary conditions, forces that apply to the object, and perform. It's very simple example, but and then we perform the finite element analysis to get components of stress, or no, like this one misses stress components. It's simple plate. I cannot find very quick examples. And so on. So that's all from my end. It's very great pleasure to do such lecture for you. Thank you for your attention.
Thank you. Thank you for Mr. Sergi. Maybe any audience wanna ask question, you can write in room chat, or if you can raise your hand. Yeah, just a moment, please. I will waiting for a question. Oh, we have first question from Mr. Adi Nugroho. From Mr. Adi, you can say something.
Can you hear my voice?
Yes,
Okay.
I can.
I would like to ask about your equation. I know that usually because I'm a designer, is very familiar with 3D, with 3 dimension. Usually, 3 dimension have a vertex. Create triangulate or square point in the 3D object. From as see on your equation, I don't see where the position of the vertex, the triangulate vertex.
I'm not sure that I fully understand your question, but I will try to answer. We use the implicit representation of 3-dimensional object. In this case, any function should has 3 coordinates: x, y, and z.
X, y, and z. Yeah.
Yes. All other parameters defines typically geometrical properties of the object represented by the function. We suppose that any function in our case, in our modernist approach, is greater than 0 for in any internal point of object, and it's equal to 0 in the boundary points of object. For example, let's see the sphere. It would be equal to 0 when x or y or z is equal to radius. For example, x equal to radius to r, y is equal to 0, z is equal to 0. Divide r in second power, divide to r in second part, we get 1, and finally we get 0. So we will get the point that we have boundary point. If we set all the 3 points to 0, then we get 1, and we will have internal point.
Okay. Maybe I still have to. Maybe can you share your presentation, maybe, or your research for us in the future? Your presentation and maybe a bigger information, maybe like your journal to us.
Yes,
Your
no problem.
journal. Okay.
Maybe I will send the presentation.
Okay. And I will like to ask. I guess you write your code using JavaScript. Is it JavaScript for the
in my software?
Yeah. Is it JavaScript?
It's not JavaScript itself. It's very similar. It's development by me language. This language supports ECMAScript standard, the ECMAScript standard, but it does not support all JavaScript functions. Yes, it's very similar to JavaScript, and as ECMAScript standard, it the same in many, but it has additionally embedded functions like this one, for example, if we open any, for example, any shape definition like this, disjunction, conjunction, additional function embedded in the language.
So it's your software, I guess. Yeah, it's your development for the software.
Yes, yes. I developer of the software.
Okay, cool. Okay.
You can see this code it's
yes,
completely.
I see the code. Yes, the code is I think it's just like a JavaScript or C++, but it's your development. And maybe for the in the future, will it have maybe more efficient than the 3D development in the into the in the 2D technology? Is it more efficient, or maybe it's more simple for to build 3D in the internet in the web? Maybe what is the benefit of this equation?
The benefits of such equations that we get representation of complex objects like this GR, for example, in one equation, and we can easily check this printed object initially was defined by just one equation. In language, in the language like this one, I can show you this example. For example, GR. Like this one. This example defines GR. This is in my domain specific language, a completely defined language. I can easily check any size of this object, any dimension it, just changing variables in my language. But finally, this language translated in one equation by my software, and I can use it to for further finite element analysis and so on.
Okay. I guess I know what you mean. This is a new technology, I guess, your equation, and this is designed to create object with simple with one equation to make complex object, I guess. Okay, thank you. Okay, that's my question. Okay, thank you for Mr. Kovarov.
Thank you for your question.
Okay, thank you. I think we don't have no more question. Maybe we can end for this event today for Mr. Sergi. Yeah. I hope for their information will be will be get information for our audience. Yeah. I will say I'm apologize with if I have a mistake. I will say sorry. Thank you and see you in the event next event. Thank you so much. Goodbye. Thank you for Mr. Sergi. Thank you everyone.
Thank you for your attention. It was a very good experience for me to take part in two lections with so good auditory, with so good listeners, with good discussion. I'm very happy that I had such ability, and I wish you to have good speakers and good students in your universities, and to grow in the mean of scientific growing, of intellectual growing, and to get always happy graduate students from your university. Have a good luck.
Yeah, thank you. See you. Bye. Goodbye.
Bye-bye.
Yeah.